Hi, my name is Gege Wen. I am from the Energy Resources Engineering Department at Stanford University. In this presentation, I will share with you our work series, CCSNet, a deep learning modeling suite for CO2 storage. Carbon capture and storage, or CCS, is a technology that injects supercritical CO2 into subsurface geological formation for permanent storage. The goal for doing CCS is to reduce the amount of CO2 that we emit into the atmosphere. In 2021, a record high of 51 new CCS projects were announced in the US. So in the near future, CCS will become one of the most essential components for climate change mitigation. Once we inject the supercritical CO2 into the subsurface, it will lead to a series of physical responses. First, it will form a gas saturation plume like the one shown in this slide. Because CO2 is lighter than formation water, it will naturally migrate upward and accumulate under low permeability barrier. At the same time, the injection will lead to pressure buildup around the injection well because CO2 is pushing the formation fluid away. Both gas saturation and pressure buildup are important behaviors that we need to monitor in order to ensure the injection is safe, the CO2 stay in place, and we don't accidentally fracture the formation. Numerical simulation is the essential tool for solving CO2 storage problems. However, they are very time-consuming. On this slide, I'm listing out a few of the challenges involved in solving these numerical simulations. For example, the CO2 storage problem has highly nonlinear governing PDEs. There's multiphysics in the problem. There are multi-scale heterogeneity. And this problem also requires high grid resolution to resolve both the physical process and the heterogeneity. And very importantly, there is the inherent uncertainty in the subsurface geology. Therefore, these problems require repetitive forward simulation to deal with the uncertainty. These time-consuming numerical simulation greatly limits our ability to find the best sites and make the optimal engineering decisions. To tackle these challenges, we developed the CCSNet. CCSNet is a family of machine learning models to serve as a numerical simulator alternative for cases that can be well represented by 2D radial model. 2D radial model is the most common case for CO2 injection into flat salient formations. On this slide, I'm showing a schematic demonstrating the workflow of this tool. First, we define the scope by listing out the inputs that would normally give to a numerical simulator and the output that we want to get from the numerical simulation. We summarize the input into 4 categories: reservoir condition, geological model, rock property, and injection design. We sampled wide ranges of input from each category to cover nearly all realistic scenarios for potential CO2 storage sites. Then we define the essential outputs for CO2 storage, including CO2 plume distribution, pressure buildup, mass balance, solubility trapping, as well as sweep efficiency factor. And then we design the CCSNet with a sequence of machine learning models to predict all of the outputs on the right-hand side. So in order to train these deep learning modeling suite that I showed on the last slide, we need to generate a data set that is diverse enough that it can cover nearly all realistic scenarios for CO2 storage in salient formation. That way we can, after the training, we can make this tool a general purpose alternative for numerical simulator. So the data set contains 20,000 input to output mapping. And for CO2 storage problem, luckily we have ideas of what kind of reservoir we'll be using for CO2 storage. For example, we know that the CO2 needs to be injected to below 800 meters for the CO2 to be in a supercritical state. And we also know that we rarely inject the CO2 into deeper than 3,000 meters due to operational cost. So that way we can limit the range of pressure that we sampled from 100 to 300 bar. Similarly, we can sample each of these parameters listed on this slide. For example, temperature, formation thickness, relative permeability, capillary pressure. We know what kind of rock that we will probably inject to, and also we have an idea of what kind of injection rate and perforation interval is possible in the real life. And also, we created a large variety of different permeability maps, anisotropy maps, and porosity maps. To generate these maps, we used the Stanford geostatistical modeling tool. And to make our maps diverse enough, we sampled from a very large range of different permeability mean, permeability standard deviation, correlation lengths on the radial direction and also the vertical direction. And we also sampled different appearance for the map, for example, Gaussian, von Karman, and we also have some homogeneous and some purely layered cases. That way, we have created a dataset that is diverse enough that can describe nearly all realistic scenarios for CO2 storage in a 2D radial reservoirs. So after we have obtained this data input combinations, we then run a state-of-the-art numerical simulator Eclipse by Schlumberger. And by using Eclipse, we can obtain the output that are corresponding to these input combinations. And on this slide, I have the example for the output of gas saturation and pressure buildup. And for each time step, the gas saturation and pressure buildup is shown as an image. And when we stack these images on the t direction, we have gotten this temporal 3D volumes. And the last step in the data generation was to configure all of these input and output into these temporal 3D volumes using a transformation. And now we have gotten a bunch of input, a temporal 3D input and output, which we will then use to train our machine learning models. So there are two types of machine learning model architectures that we have used in our work series. The model on the left is a convolutional neural network. This is a temporal 3D convolutional neural network that has an encoder, a processor, and a decoder. And the left figure shows the schematic. And the encoder of this model takes the input and convolutes it to extract higher order dimensional information. The processor maps the input's higher order dimensional information to the output's latent information, and the decoder will take the output's latent information and transform back to the physical space. Although this type of architectures has been used in some other applications, in our application we have a twist where we use these irregular temporal and spatial grid. We use these because for CCS problem, the time frame that we consider is often very long, and we need more refined time snapshots near the beginning of the injection and less time snapshots near the end of the injection. And similarly for the spatial, we need higher resolution near the injection well and coarser resolution away from the injection well. So using this irregular temporal and spatial grid, we were able to consider a much larger reservoir box and a much longer time frame that can satisfy our need for predicting in CO2 storage context. The model architecture on the right-hand side is an enhanced Fourier neural operator we named UFNO. UFNO is built upon the Fourier neural operator, and we did this work in collaboration with the Caltech University and Purdue University. And the Fourier neural operator is different from CNN because it learns a infinite dimensional integral operator compared to in CNN, the model we learn is a purely empirical input to output mapping. So because the FNO type of architecture learns this infinite dimensional integral operator, it has been proven to be a lot more data efficient in many different problems. And in this work, we have extended this FNO into the multi-phase flow CO2 water multi-phase flow context, and we have proved that the UFNO has a lot better accuracy and data efficiency compared to the state of the RCN. It requires only about 34% of the data, the training data, as in CN, to achieve the same testing result. On this slide, I have a few examples showing the accuracies of the models in this work series. On the left column, we have an example of the saturation prediction. The top figure is the heterogeneous permeability map. The second figure is the numerical simulations prediction. The third figure is CCSNet prediction, and the fourth figure shows the absolute error. From these visualizations, we can immediately see that the prediction of CCSNet is very accurate for the saturation. And besides the visualization, at the bottom, I'm also plotting the numerical simulation versus CCSNet on each single grid on this scatter plot. And the color of the dots on this plot shows the period of the injection. So from this plot, we can basically see that the prediction is consistently good from the beginning until the end of the injection. Similarly, in the middle column, we have the pressure prediction. The top figure is the geology, and then we have the numerical simulation and the CCSNet prediction, and also we have the relative error. So the bottom scatter plot also gives us the same information that the prediction is very consistent from the beginning of the injection to the end of the injection. The example on the right hand side is called SCO2. This is the molar fraction of CO2 dissolved in the liquid phase. And this prediction is slightly different from the saturation and pressure because they kind of have a binary effect where when the separate phase CO2 plume touches the reservoir, a portion of the gaseous CO2 will dissolve in the formation fluid, and the dissolution rate depends on pressure and the temperature in the reservoir. And at the leading edge of the plume, there is also a small area where CO2 where the dissolved CO2 migrates in advance of the plume, and that forms this colorful band at the edge of the plume on the right hand side. Although this behavior is a little bit different from the saturation and pressure, the model still manages to predict very accurate results. So besides having visually resembled prediction to the numerical simulation output and having very high R-squared score, we also want the predictions to obey the governing law. And that's why we evaluated the mass balance. So mass balance is a critical measure of how well the model's prediction obey the governing equations. And here I have the equation for calculating the mass balance, which is the summation of volume times saturation times pressure times mass fraction of CO2 in the liquid and gas phase, and then times density. So the saturation is predicted by the saturation model. The porosity is predicted by the pressure model because the rock is compressible. We also have the molar fraction and density predicted by the molar fraction model and density model in the prediction sequence. In combining all of these outputs together, we can calculate the total CO2 mass, the liquid phase CO2 mass, and the gas phase CO2 mass. On the bottom three figures, I'm showing the mass error percentage for the CO2 in the liquid phase, the gas phase, and the total. And from these figures, we can see we have 95% confidence that the prediction error of the mass is within plus or minus 1.5%, and that is enough accurate enough to support applications such as site selection and some engineering decision making. So using these models, the biggest gain that we're getting is the speed. CCSNet can generally provide 4 orders of magnitude speed up, and in order to demonstrate the speed up, we host these pre-trained models on a web application called CCSNet A. And this web app is available to everyone through the internet, so if you want to check it out, just type CCSNet A in your browser. So in this little demo, I'm showing an example of me trying to figure out where would be the best location for me to inject so that I can get the highest swoop efficiency factor. In conclusion, CCSNet is a deep learning modeling suite that can serve as a numerical simulator alternative, and we will use this tool to support the scale-up of CCS projects in the future. Thank you so much for listening.